In this brief presentation, I'll show a robot can estimate the mass and center of mass of unknown bricks and use that information to build an overhang stack. In many real-world scenarios, such as warehouses, robots must stack objects without knowing their exact mass or how their weight is distributed inside. So my goal is to have the robot deduce each brick's mass and center of mass, and then use these estimates to achieve a stable maximum overhang configuration. And when I consider a simple scenario with no internal mass offset, the placement strategy to keep the stack balance is relatively straightforward. However, when each brick's center of mass can shift away from its geometric center, the placement becomes trickier. In fact, this internal offset means I have to carefully reconsider how far forward I can push the next brick, and I need to keep adjusting how I choose the placement positions to maintain stability for each brick. But ultimately, the first challenge is to determine each brick's mass and center of mass. Let's see how the demonstration works. I have a simulated environment with a brick's mass and center of mass being unknown and slightly varied from brick to brick. Notice how the arm picks up the brick and holds it in the midair, and the robot arm makes small movements to gather data. By doing so, it observes how the brick influences the robot joint torques, and the system can infer the brick's mass and internal weight distribution based on that estimates. Specifically, as the robot holds the brick, gravity pulls on it in a way that produces measurable torques at each joint. And as I adjust my best guesses for the brick's mass and internal offset from each joint in different poses, I get closer to the measured torques. To get these estimates, I take torque measurements at several arm poses to collect enough information to reliably guess the mass and center of mass. Then, I can start planning the brick's placement. The goal is to push the stack further out while staying stable. And for each next brick that I want to stack on top, I can figure out the kind of safe maximum position for overhanging through these math equations. And I keep iterating this process, estimate the parameters, adjust my placement, and ensure the stability when stacking. However, since the real-world stacking position isn't perfectly aligned with the estimation, I applied a safety factor. One of it is placing the brick slightly less aggressively than the maximum would suggest. So this ensures I don't end up with a fragile tower like this demo. And during my testing, about 4 out of 18 trials failed because the gripper slipped, causing the brick to tilt and ruining the estimation. However, still, the overall performance shows promise. But of course, we can do it better. For future work, I might incorporate additional sensors like camera to recognize shapes and anticipate slipping, or adjust my strategy dynamically if the robot senses something amiss. And finally, as a fun touch, instead of having the go home as the final phase, I implemented a phase where the robot breaks the stack bricks, causing them to topple, and the robot has to pick and stack it up again. This is the end of my presentation. Thanks.